My name is Kyle Messier. I'm a Kravis postdoctoral fellow with the Environmental Defense Fund and the University of Texas at Austin. So about 2 years ago, EDF, UT Austin, in collaboration with Google and some other partners, equipped a couple of Google Street View cars with laboratory-grade air quality instruments, and they began driving around Oakland, California, collecting high-resolution air pollution data. This is in contrast to the standard method of collecting data, which are stationary monitors, and at best there's a couple per city. So in good timing with this summit last week, with the release of our journal article, EDF and Google both prepared websites and blogs, as you can see here, and we got a decent amount of press out of it, which was nice as well. So that was phase one, where we created maps based on those observations. Now, where we bring in Earth Engine is we want to expand our maps to unmonitored locations as well, because we can't be driving these cars around everywhere all the time. So we implement land use regression, and simply that is using spatially referenced data as explanatory variables in linear regression analysis. So it's not a terribly complicated model. But as an example, you can see here that we'd have an explanatory variable such as a percent developed land within a buffer of X size, or in DVI. So the variables we calculated in Earth Engine include percent land cover variables from the NLCD, and DVI, elevation, impervious surface, and then also some point source variables that were brought in, national priority listing, toxic release inventories, and also distance to ports and airports. And then once we have those, we brought those out of, currently we do the modeling process outside of Earth Engine, did a model selection process, and on the right here you can see our final model explaining the concentration of log transform NO. And I'll let you look at those. I don't have time to explain them. And then we can make some nice maps. And so here we have the predictions based on our model and observations of NO. And so here you have, on the left side, you have West Oakland and downtown Oakland, and then the highways, that's Highway 880 and 580 on the north, and then East Oakland. And then the polygons represent areas we held out for test and validation samples.
How do you handle the time dimension of your data? Like, you can imagine during the day between rush hour or peak of the day with more or less sun, will we have different levels of pollution, and we didn't see that there?
Sure. This is a purely static map representing what we call the representative annual average during daytime and weekdays. We use a stationary monitor to adjust diurnal variation, so the within the day variation is adjusted. Our 1 second measurements. And then these represent, I failed to mention that these maps are at about a 30-meter level. So we took all the roads, reduced them down to 30-meter points, and then as all our measurements over the course of a year, the closest, that 30-meter point was brought to there. So we have between 100 to 200 1-second measurements that were reduced down to that. And we calculate a median or a mean. You can calculate any statistic you want. But those 1-second measurements were adjusted diurnally. And since we sampled over a year, we had roughly equal sampling across seasons as well. But one of the next steps we want to do is develop space-time models with that as well. So these would vary over time. And also, I'll let you know, all that space in between, we just had those variables in the final model calculated in Earth Engine. So it'll soon to be filled in all that space in there.